Good morning, everyone. Thanks for joining us in this workshop on cloud, and the future of work. My name is Besmira Nurshi. I am a researcher in Microsoft Research AI, and today I'm co-organizing this workshop together with Vani, who is Director of Data Science in Microsoft Research Outreach. And for today, we have put together an agenda of 6 exciting talks, all centered around the topic of large-scale crowdsourcing and citizen science initiatives. And before we move on with the agenda, I'd like to spend a few minutes trying to frame a little bit the conversation for today and even the breakout session maybe a little bit later on. So crowdsourcing research on citizen science is now at least 10 years old. In fact, the first human computation workshop happened in 2009, hosted by KDD back then in Paris. And in these last 10 years, we have seen at least a few initiatives that have been successful in creating large-scale projects, either for unpaid crowdsourcing, like citizen science or others. And in fact, today we're going to be lucky to hear updates from some of the most representative ones in the field today, like the Human Computation Institute, Zooniverse, and BrainLife. But what I wanted to point out as well is that usually around this project, large projects, there is an extended landscape that supports the development of these projects, and I would like to touch upon that. So, of course, in the last few years, we have seen a lot of effort going into building platforms for citizen science. And the top 2 challenges in the space of building infrastructure that supports collaboration have been to design good incentive schemes for having workers to provide high-quality work. Now, from a research point of view, it might seem like these are problems of the past. It might seem like we have solved all these problems in conferences and papers. But the truth is that they remain challenges today in practice, and they can become important factors that define whether the life of a crowdsourcing project is going to be long or not. And which is why I wanted to bring them back today so that we can hear more about what do these challenges look like in practice. Next, eventually the data that is collected with these crowdsourcing platforms is being used to eventually train a machine learning model. And the long-term topic of discussion in both the machine learning and the crowdsourcing community has been how can we actually train machine learning models with imperfect human input. And beyond that, we would also like to have these machine learning models to be put back into the crowdsourcing frameworks in order to reduce the cost and the effort of crowdsourcing. And while, again, we have discussed this multiple times on how to build hybrid systems and human-in-the-loop systems, these techniques of putting back the machine learning models in a way that they can reduce the cost of crowdsourcing have just started to be used in practice. And next, obviously, the long-term goal of building all these models is to have them assist the experts in the decision-making, or even help the scientists in pushing forward the boundaries of scientific research. And in this space, I call it under construction, and it is under construction because we still do not understand very well what are the properties of a good machine learning collaborator. What does it even mean for a human to work in this environment, working with one or many machine learning models, and to understand what is the role of the human and how can the human make sense of all these signals. And moreover, we want experts to be introduced and to be fused into the crowdsourcing framework so that they can give feedback to the data collection process, so that the data collection process can be reshaped in a way that the models that we are going to train in the future can actually be helpful to experts in the decision making. So I'll leave it to this picture. I hope I'll hear more about these questions during the talks and during the breakout. And we're going to move on with our agenda. The first speaker is AJ Kamar. AJ is a principal researcher in the Adaptive Systems and Interaction Group. And she's going to talk about how can we enable AI development with human intelligence. Thank you.
Good morning, everyone. Let me tell you a little bit about myself. I did my PhD like years ago at the intersection of AI and humans, thinking about how AI and humans could collaborate on complex tasks. Then I joined MSR like 9 years ago. It was kind of the time that crowdsourcing, human computation was just being discovered through platforms like Amazon Mechanical Turk, Citizen Science. And I kind of find myself so excited about this large-scale, scalable access to human intelligence on these platforms. And over the years, we've looked into so many different problems in this space with our collaborators like Lucy from Galaxy Zoo's Universe and others, UHRS, our own platform at Microsoft, thinking about how to make crowdsourcing high quality, how to get people working on crowdsourcing engaged, and so many different problems. For today, though, I really want to think about the role of humans, in particularly the crowd, in the development of machine learning systems. I'm going to kind of take that perspective because this is a very rich space, and I could give many different talks today. I kind of just picked that perspective for today. Just thinking about, like, we always think about machine learning platforms as this very data-centric kind of mechanical process for building systems, but is it really that way? And what kind of algorithmic and workflow style innovations we can do in that space to make it better? So you've seen these kind of slides at every AI talk. There has been a lot of advances, mainly in perception tasks, now getting into the language for many tasks. But we are also seeing that existing AI algorithms fail in different ways, fail in unexpected ways. Sometimes they fail, correspond to problems that we have in the society, corresponding to disparate impact for different genders, ages, races, and so forth. Sometimes they lead to reliability issues. For example, when a self-driving car or a physical robot fails in the world. And a lot of the time I spend these days is really thinking about these kind of reliability bias problems and thinking about ways to overcome them. And I really think that if you try to uncover the pipelines and workflows for developing AI systems and really look into them, really try to understand what happens at every step of the development workflow, that gives us good clues about how we can improve this process in different ways so that we can lead to more reliable AI development. So what I mean by that, when you ask a machine learning researcher about how they are building a system, they are going to give a workflow that's very similar to the one on the top. They are going to say, okay, I have this beautiful data set. Somebody has collected this for me or for something, or that's available on the internet, so I'm just going to focus on that because that's readily available. I'm going to get that, find a problem that works well for that data set. So it kind of works the opposite way. You would really like to know the problem and then collect the data. Most of the time it happens the other way. And then they divide the data. It says, this is my training data, this is my test data. Really focus on the algorithmic innovations, on like how many layers of the deep neural network it's going to be, and how the parameters are going to be, and how the dropout is going to be, and so forth. And then they get this really beautiful model, very sophisticated, tested on the test data that comes from the same distribution as the training data, evaluate it, look at the aggregate number like an accuracy, say, score. I've done great. My numbers look better than your numbers. This is a great system. However, real-world deployment of AI systems look quite different than that, right? Our workflows are very different. First of all, this training data doesn't really come from sky. Actually, on some surveys that Besmira has been involved in as well in our department, we actually see that 90% of people's time go in real deployment scenarios, go to tasks that are not about model training. It goes to data collection, data cleaning, debugging the models, and so forth. So this step of training is a big step in making our machine learning models work. And there's, of course, the data in most cases come from humans, sometimes from crowdsourcing, sometimes from user data. Then we have a lot of human involvement actually in the development stage. A human decides what the objective function is going to be. A human is going to decide what the interaction is going to be. And the human is going to be deciding how to evaluate the system, what is the safety criteria, what is the reliability criteria, what is the bias criteria. And of course then, when we push these models into the world, in particular if there are reliability problems, it is better to have humans involved to watch over these systems and correct them when they are making mistakes. And then finally, we really want to watch these systems all the time and see where they are failing and get through this continuous feedback loop and improvement loop. And of course, a lot of engineering and data science people are involved in that process very heavily. So it's actually misleading to think about the machine learning pipeline as the one and on the above, where we only focus on the algorithms. But we have to acknowledge that people and many different types of people, including the crowd, including the developers, including the data scientists and users, are actually part of this development loop. So today in this talk, I really picked a few projects we've done over the years where we are touching different points in this workflow and show how we can have algorithmic workflow innovations in some sense to actually make that process better, and just to show examples of what kind of work we can do in that space. And then I'm going to finish up with some things that is top of mind right now for me in terms of thinking about these workflows and the crowd involvement. So this is a slide from 2001, so a lot has changed since then, but I think the common trend still stays. The fact is that we really celebrate algorithms, but to get algorithms work very well, we really need a lot of data. And this is more true today than ever with large-scale deep neural networks that are really, really data hungry. So actually, even in the latest celebration of AI, actually the hidden hero has been crowdsourcing workers. They have done all of the work that enabled that with the COCO data sets, with the image nets, with the large-scale data sets we are collecting from the internet today. So it is really important to acknowledge the human effort that went into making these machine learning models really successful in the last decade or so. One thing we've looked into, I think this is where we started in 2012, was thinking about label collection in crowdsourcing, which is a core task when you're doing image data sets, language data sets, anything like that. And really think about, given that there's going to be a big demand for human input to construct these large-scale data sets, how can we make this process more efficient so that we can be more respectful for the human time? And this also is a big concern for a citizen science platform like Zoo Universe Galaxy Zoo. So this is why we collaborated with them on this project back then, because for them, the amount of citizen scientists really determine how much data is going to be collected for science, which is going to be determining how much insights and innovations are going to be found for astronomers, right? So in this problem, what really happens is that we have a task coming in. We can use machine learning algorithms to generate initial hypotheses about what the label is going to be. This task is quite simple. This is the original Galaxy Zoo. You have an image of a galaxy, and you're trying to classify this image into 6 different classes. Of course, the machine analysis on this task is going to be just a weak evidence for what the true label is going to be. So you want to query multiple people, but each person in a paid crowdsourcing setting may cost money. In citizen science, it's going to cost people's times, right? You want to be careful about that. And there are some questions that we looked into this project. How do we fuse automated analysis with human input so that we can get a lot of the work done with machine learning? Can we learn which citizen scientists are more accurate for which tasks so that we can put more emphasis into their answers and get to the true answer more accurately, more quickly? And can we do retirements? Because this was the biggest problem they were facing. I think still it's a big problem for the platforms. You really don't want to put 30 people on every single task because maybe some things are quite easy or some things are unsolvable, which is also a case in here. So this is when we built the crowdsourcing system, where we had this workflow that combined multiple machine learning models with a decision theoretic planner that worked in synchrony. The machine learning models learned about the tasks, task characteristics, which tasks are hard, which tasks are easy. Also learned about the citizen scientist, which one are better at what task. And then all of these inferences, including the machine inference about the task, went to a planner where the planner did decision theoretic analysis at every step and asked the question of, if I got one more citizen scientist into this problem, would my answer change? And with this, we actually show that we could get the accuracy of the original system by only spending half of the human resources. There's actually this doubling of the efficiency that we could see with this platform. So I think a lot of these ideas are still pretty valid for the crowdsourcing systems we have today. And some of these ideas were then actually implemented in our internal platform, UHRS. Those were the case for the objective labeling problems. There's a galaxy, there is a ground truth answer, hopefully you assume that it exists, that we are trying to give to the astronomer. But then when we were working with different product groups, we realized that in a lot of cases, the tasks are subjective. A lot of the community kind of assume that there is this one ground truth answer that is true for all humans, but actually for many labeling tasks, like for example, relevance judgments in Bing, we saw that that wasn't the case. Even for something like this, like you have a bunch of images and you're trying to classify whether it's a cat picture or not, a favorite problem for AI world, right? People, when you get into the instances, you could actually have a lot of subjectivity. Is a cartoon cat a cat? Is a cat machine, like these work machines, is that a cat? So when we got into the nuances of the data set, we realized that people were writing like 50-page instructions for crowd workers just to kind of convey their idea of what a cat is. And it was becoming a really cumbersome process for workers because people had to look into the data to create all of these, like, okay, I guess a cartoon cat is a cat. A picture of a cat is a cat, but the work machine is not a cat. Right? It was very cumbersome. But it was also really bad for workers because workers were doing an honest job, but then if the instructions missed something, they were being penalized for giving the wrong answer. However, they weren't really giving the wrong answer. So we said maybe we should just look into this process completely differently. And this is when we did Revolt. This is in collaboration with Salim Amarshi. So what we said is that, look, let's change the way we do crowdsourcing. Let's make it interactive. Let's get the crowd really talk about what they are seeing. Maybe through that, we can actually enable these rich data structures that can really capture the uncertainty that exists in data. And then we can really show that uncertainty to the requesters, and they can decide what to do with that data. So that's what Revolt came out to be. We get the unlabeled data, and we get through an interactive crowdsourcing process now. And we built through the years some tool sets that enable this kind of interaction with the crowd workers, with the CogBot project, and so forth. So in the first step, crowd workers label the instances. And if there is a disagreement, they explained why they thought the answer should be A or B. And then we used other crowd workers to look into this rich data now with crowd explanations and build clusters, start categorizing them. And what we ended up is actually this rich data structure where we could see clusters for cartoon cats and clusters for pictures of cats and clusters for other things. And then this data actually then became reusable for different purposes because somebody who wants to train a classifier for live cats could come and select some of the instances as positive and some of the instances as negative. And somebody may come and do a different decision boundary and train a classifier, train a different classifier. So the data set actually became reusable. So what we showed with this work is that when you put interaction into crowdsourcing and enable the collection of more sophisticated responses rather than labels, you could actually require drop the requirement on requesters to create these 50-page guidelines. It became better for workers because they weren't penalized for giving the wrong answers, uncertain answers, and we could capture this restructure that then later can be used for different purposes, including debugging, where the models fail. And then we said, okay, let's get a real-world AI system and think about how we can use the crowd to complement the system during execution, not in training, but in execution, interaction with real people, and see how this crowd involvement can be good for addressing some of the reliability problems. So we looked into the image captioning system, which was actually a well-celebrated AI challenge in the community where Existing papers show that these systems got so better that they were better than humans and all of that. And we wanted to see whether that was really the case and how human help can be useful to help people when they were using these systems, which actually exist today at Microsoft as the caption bot. And we've done experiments where we showed, and these were experiments were done with blind people, because when you read a lot of these papers, you actually see that they provide the assistant to the blind as the motivating scenario. So we wanted to see how much value they were really getting out of it. And what we showed was that for blind users, just giving the system to people was actually really bad, led to terrible satisfaction. And you can see this from this picture. Here, this is a time tweet that says, it's basically people really upset about the crash. And the caption given for this picture automatically was a man sitting on a table, which really didn't help. But then when you brought people in different ways, either correcting it with an offline task or getting into a dialogue with the caption bot, you could see the performance going up and people are really getting a satisfactory experience. And then later we can use that human data to improve our systems or generate some templates that can be used across different people for a better improved caption. The last thing I want to mention is the work we've been doing on troubleshooting and debugging of AI. This is another area where we can use crowd input to really inform our models in terms of how they can get better. So this is actually the work that Besmir Nishi has been leading on troubleshooting, debugging. We did a demo of a simpler system yesterday that we are working with product groups with. But on a research side, we've been looking into using the crowd for debugging of integrative systems that are composed of multiple components. And before, as an engineering team, you decide where I want to invest my efforts, you could actually use the crowd to simulate different improvement approaches team has come up with to simulate what the performance would be once you invested into these improvements. And get graphs like this where you could really speculate like, okay, I have this integrative system with 3 components, let's say. Where should I spend my improvement effort? How much improvement in the final system output I would get if I improved the visual detector, the language model, or caption re-ranker, or all of them, or even simulate different fixed ideas on that. So just finishing up with some next steps, open problems, at least for me in this space. We really want to think about how we can use humans to understand deeper problems in machine learning models, getting into biases, getting into blind spots. This is something we've been investing time into, but I think this is an important space as we are building these machine learning models that are going to be important for many real-world tasks like health and other domains. We really need the human help in understanding where they are failing or how they can get better. I think the crowd platforms provide a beautiful platform to understand about human judgments, how humans make decisions. Kind of they can provide a lens for us to really analyze the human side of things as well. And Andy has been doing, she's not here anymore, but she's doing a lot of work in that space, understanding human biases through crowdsourcing, and she can tell you more about that. One step that I didn't talk about today is that in the development of systems, we have humans providing value judgments, thinking about the ideal behavior of the system. We see a lot of discussions about this in self-driving cars and so forth, like, there's the moral machine kind of ideas. But I think when we get into the engineering pipelines, thinking about how we are going to be deciding what these systems ought to do is a big task. And then there's actually a lot of issues around ethical side of data collection. We see that this when we are doing data collection for accessibility. Is it fine to grab data from the internet? What does consent mean when we are doing data collection and so forth? So again, a rich space of problems. So I'll stop there, and if you have any questions, if I have time left, I can do that, or we can talk during the day.
Okay, let's take one question while we set up Corey.
Yes, Pietro.
No one else has anything to say. So I love this idea. Yeah, sorry. So this is great. So I need to turn it on? Oh, okay.
Yep.
So it's really great overview of a lot of really interesting work, so thank you.
I went so fast, so come and talk to me if you want to hear any more about any of these
Okay,
projects.
okay. Yeah, so the one thing that really piqued my interest is this idea of kind of inserting humans into the pipeline at different places where you're trying to decide where do we place our efforts to improve the pipeline using an automated approach. And so it occurs to me that you might identify in the course of doing that there are certain areas that could have the greatest impact. Mm-hmm. On the other hand, there's another dimension of that, which is that each one of those places in the pipeline has a different sort of level of challenge associated with achieving that kind of capability in an AI. So I'm wondering, how do you do that kind of assessment in order to be able to then decide what the cost-benefit analysis is?
That's a great question. I don't think we have the level of maturity of understanding in this space to really do that right now. The fact is also that in terms of those human involvements, the actors could be different. So you could do some things with the crowd, but for some things you may need the developer time. For some things you may need to bring in an ethicist to really answer questions about the value judgments, and the availability of these resources may also be different. So I think one way we are thinking about this is really trying to build tools to give to people as they are building the AI systems. I think we are really early on that, but we have been doing bits of work here and there so that people who are building these systems can decide, okay, at least I have the tools to do it. Then you can reason about what is the scale you want to do it, when you want to do it, with how many people you want to do it with. Thank you.
We can take one more question. My computer went.
I'm turning my microphone on.
I didn't know what it was. Thank you. That was really, really interesting. I have a question on the cultural aspect. If there are studies which involve some cultural aspect. What I mean is, like, when we look at the data on the web, is very multilingual, and so more probably because people come from different cultures, right? We come from different countries, and we still use English. And so I'm wondering, when people label, if the cultural aspect may have some impact. For instance, I see a picture, somebody could say this is an emotional hug, and somebody else would say, I don't know, something else, right? Stiff upper lip, I don't know, something. Are there studies on that?
That's a great point, and that's actually one of the motivating things for us to focus on the subjectivity and kind of collecting rich data and not limit crowdsourcing to this label aggregation world where there is one truth and we only try to seek that one truth. But we actually acknowledge that people have different opinions, and we can get them talking and providing that complex data, and then we develop methods to make sense of that data. But I think overall there's another question I'm really thinking a lot these days about, which is, as we are putting more AI into people's work, for example, like AI writing sentences for people, AI writing captions for journalists, AI doing all of these things. We know that these systems are really good at learning major patterns, but they don't really capture the diversity we have in our world, like the diversity of different cultures, diversity of different perspectives. So are there things we are going to lose if we just let AI to do a lot of these things about capturing our beautiful diversity? And I think that's why I really want to focus on these hybrid workflows where we can really capture the human, perspective, but have AI kind of helping with maybe the boring part or the part that doesn't really require that human ingenuity, human intelligence. So a lot of work to be done in that space, I think.
Thank you, Ajay. So next we're going to have Corey Inkpen talk about human AI complementarity.
Thanks. Mike, okay? Okay. I'm really excited to be here today. Just like AJ started out, I'll give you a little bit of my background. So I spent 10 years researching face-to-face collaboration, looking at tabletop displays, wall displays, things like that, in academia as a professor. Then when I came to Microsoft, I spent approximately 10 years looking at distributed collaboration, connecting people over a distance using video. And now recently, I am starting to look at another form of collaboration. So this time looking at human-AI collaboration. So this is a new thread of research for me. I'm really excited about it and love to make new connections in this space. So today I'm going to share some of my early thoughts on human-AI complementarity. A lot of the things we're talking about, I work very closely with HA and BESA, and I have some rock star interns and an AI resident. So a lot of the ideas that I'm sharing here are things that we've all sort of been brainstorming and talking about together. So one of the things that we've been talking a lot this summer about is the best AI really the best AI? So if I'm building an AI system to be run autonomously or to do the task completely, then yes, I probably want to maximize the accuracy or the F1 score of that AI. But if that AI is going to be deployed into a workflow that has humans, do I really want to be maximizing the accuracy? Do I want it to be doing the same task as the human? Maybe we need to dig a little more deeply and look actually at the workflow of the task to decide what are the best things that maybe the AI should do, and what are ways that it can complement the human. So that's one of the things that we are starting to look at this summer. And so we're thinking about complementary abilities. And I'm going to give you a couple examples here. So let's assume that I am a lab technician, and I'm really good at identifying whether a cell is cancerous. And I'm very accurate at this, so I have high accuracy on this. But I do so many scans in a day that I miss some along the way. So my recall is a little bit lower. In that case, maybe we should be looking at building an AI that actually makes sure that it shows me all the potential places I should be looking so that I don't miss any. So we might want to optimize the AI for recall. So now if I take a different hat and I'm now some sort of astronomer, and I'm really good at detecting flashing lights in the sky. So my recall is really great, I never miss one. But I have a trouble deciding, well, is that some sort of meteor? Is it an airplane flying by? I'm not very good at that. So maybe my AI needs to be optimized for precision for those types of tasks. So those are two toy examples, but it shows you that how you want to build your AI to work with a human depends a lot on the task and on the context. My clicker is not working. Okay, I'll go the old-fashioned way. Or my computer is not working. Oh, it was just stuck. Okay. Now I want to give an example of non-complementary or non-collaborative. And we see in the news all the time examples of AI being deployed in the real world. And this was one from a year ago. And so the ICE immigration system has a risk assessment software. They enter information for the people that they find, and the system is supposed to give you a recommendation as to whether you should detain that person or release them. So it gives a risk factor. Well, in a changing political climate, a year ago, it was reported that this algorithmic system still is in place, was still being used, but it has one decision. It always says detain. And so this is an example where having a system doesn't even make sense, and it doesn't at all work with the human. Now the news article goes on to say, but the human can override it anytime they want. Although I'm not sure how often the ICE official is actually going to override the system. So that example is to lead into this idea. The examples I gave you before about the cancer cells or the astronomy problem dealt with complementary in terms of performance. But it's a lot more than just what am I good at and what am I weak at. It's also what are the human factors that influence how well the system gets used. Do I trust it? Do I believe in it? How accountable am I? If I'm a judge or a doctor, I may feel perfectly comfortable ignoring the system and the recommendation it gives me. If I'm a lab tech, maybe not. So it depends on my role, it depends how much authority I have, it depends, even the instructions that the system gives me is going to influence how I feel about it and how I engage and interact with it. And there's a whole host of questions here that are still completely open research questions. Like, we don't fully understand how to deploy these systems into the real world and for people to be able to engage with them. So this is a graphic I like to show of this space that I'm really interested in working in. So I'm obviously interested in human-AI collaboration. But I'm interested in these complex problems where the AI knows a part of the world. And it has its data set, and it can learn complex patterns within it. But the human knows a part of the world as well, and it's slightly different. So we overlap. We might know the same data that goes in, but I, as a human, don't understand the complexity of the model. But I know other things about the world, and I have other experiences that I rely on. And so truly, we want to have these two systems work together. The other thing is I also want this to be evolving over time. As these things get deployed, we need to have a feedback loop in here. We need to ensure that the AI is continually evolving to get better, and the human is always evolving to get better. If I override the system and feel that I don't trust it for that particular instance, I should know at some point down the road whether or not that was the right decision or not, or I should be able to learn from that. Because ultimately, we want to grow these two circles to encompass more of the world. So another sub-theme within this that I'm really fascinating about is this idea I call designing for disagreement. And again, a lot of the examples I'm giving are related to sort of human decision making. So if I'm working with the AI together and we sort of come up with the same answer, great. But what if we don't? What if we're doing something and the AI believes something different than what I believe? And I think that's a really interesting space, because that's where a lot of these human factors come into play. Do I trust it? Do I feel that I have authority to overrule it? How do I resolve this disagreement? So there's a few things that we've been exploring. And the data set that we started to look at was this recidivism data set. Recidivism is a prediction as to whether a person will commit a crime in the next 2 years. So there was a student at Dartmouth that had done a crowdsourcing study where they had Mechanical Turk workers predict recidivism for a population of defendants, and they compared the risk predictions of the Turkers with Compass, the commercial AI system. And so that was the data set that we started for this exploration. And just so that you have a sense of what the Mechanical Turk task was, they got a little paragraph about the defendant. See, not very much, but all the features are in there. In some runnings of the experiment, it gave the race, and in other ones it didn't. And then they had to say yes or no, and they had to do 50 of these trials. And then they got a score at the end. So this research got a lot of publicity at the time because all the reports said, hey, guess what? Humans are just as good as the AI system, because they both were approximately 65% accurate. Well, our research question was, are they coming up with the same 65%, or is it different? Because if it's different, then I can leverage the complementarity. I can leverage what the algorithm is good at, and I can leverage what the human is good at. And so when we looked at it, this was the pie chart we saw, not only from the Dartmouth study, but in our rerunnings of it. It essentially comes back very similar to this. 50% of the time, Compass, the algorithmic system, and the Turkers agree and have the correct answer according to the ground truth in the data set. The other half of the pie is split pretty evenly into thirds. 1/3 of the time, the algorithm is correct and the human is wrong. Another third, the human is correct and the AI is wrong. And the last third, they agree, but they're both wrong. So we're going to ignore the purple. They're both wrong for now. But if I can find a way to leverage, again, the strengths of the algorithm and the human, I should be able to increase this to be about 80%. We haven't quite solved it yet. The first approach was to try to build a hybrid model. Let's see if we can build a model that tells us, in this particular instance, take the human decision, in this particular instance, take the AI decision. We got slight improvements, but it could also be within the noise. I think the fact that it was a mechanical Turk data set is influencing this. I won't dive into, I still believe this is possible, it just isn't quite showing here. Another, and there's a lot of work in the community, I can give an explanation of the model to the user to help them understand, did I miss something, or is the algorithm missing something? Another variant on this, and I'm sure it was presented during the faculty summit, is you could look at an error analysis, and BESA and HA have a tool that they've been looking at this. So I can see, where does the model make mistakes, and does that help me understand whether or not I should utilize it here? And then we'd like to get more complex with this and enable even richer interactions. How can I engage with the model similar to I would with an expert human? Okay, if I was dealing with an expert, they wouldn't just come in and say yes or no. They would tell me why, or we would have a dialogue about it, or we would have some sort of exchange. And so I think we need to get to this point to really be able to interact well. So to wrap up, super passionate about human plus AI collaboration, but the plus isn't enough. There's lots of research that's actually starting to show if you just try to glue these two systems together, you can actually make them worse. So we do need to think about this complementarity, how they're going to work together, and what's going to make them the most successful. Thanks. Yeah.
Hi. So you mentioned that the data set that was built by the Turkers, there was some potential issues with that. Could you go into that a little bit?
So the issue is if you remember the Venn diagram where I'm interested in problems where the human has access to additional information than the model does, when we use the Turkers, we tell them these are the exact same features that the model has. So there's very little difference in the amount of information they have. My hypothesis is if we were to run this with judges, there would be a lot more information they would be relying on, which could make it better in terms of complementarity. It also might make it worse because there's bias, et cetera. So within the Turk data set, it was just that they had the exact same features that the model had.
Okay.
So there was very...
Okay, good. So you said you might give it to judges and it would be different, but what if you gave it to non-experts but with more information? Would you see also a difference?
Yes, we've been looking for data sets to be able to do that. Again, the qualitative data, things that is hard for the algorithm to understand, but a human might be able to make sense of it and it might provide information. I do think even non-experts would benefit from that. The other piece that we've done related to that, and Carrie in the back has been running this, is we took that task and we added a photo. And this was to look at racial bias. So the hypothesis was that little word related to the text doesn't have a lot of saliency. Maybe if we show them a picture of a defendant, it'll influence. And it did. It influenced it in an opposite way than we expected. So for white defendants, it made no difference whether we showed the photo or not. For black defendants, it did make a difference, and they were less likely to predict that they would commit a crime in the future. I have a couple hypotheses for why that is the case. I mean, it could be that people are trying to be conscious of their biases. It also could be that the photos we used were not real photos of the defendants. They were from a generic face data set. And it could be that the delta between the photo for certain my image of what a defendant of this race is could be further away from the photos, or the photos could be balancing it out some. We don't know exactly why, but we've had multiple runnings of it, and this trend continues to happen, that we get this benefit from humanizing it, from showing the photo for the Black defendants. So, yep. Oh.
Hi.
Yeah, that's okay.
Some aspects of what humans do in their workday and life are clearly they're not good at, right? And others they're much better.
Yeah.
Now, some of the tasks the AI can do, maybe should do, are the ones that we are worst at. So are you thinking about that component, like what we know from psychology and cognition about what humans not very good at? And
Yes. I think that's a big part of the complementarity. What is the AI good at, and what should we have it do? Another question, and I'm not a machine learning researcher, is if I'm interacting with the system a lot, can it start to learn what I'm good at versus what you're good at, and so that the tasks get segmented in a way so that we're maximizing our expertise? We may be able to utilize systems in that way as well.
Thank you, Corey. So next we have Dana Gorari, who is going to give a presentation on her work on how to recognize when a crowd will offer a different answer for visual questions. Dana has done a lot of work and recently also with, collaborating with Microsoft Research on better understanding how to build vision models for people with disabilities. And looking forward to your talk, Dana.
Thank you. Can everyone hear me okay? Yes. Okay, great. So thank you for being here. Today I'm going to talk about the task of visual question answering. So shown on the slide are 4 examples of visual questions, which are simply questions about images. And the goal is to find the answer to each question. So why should we care about visual question answering? These 4 examples highlight questions asked by both sighted and blind people. So as an example, a person who is blind may want to know when preparing food, what food to eat, what is the flavor of food when considering what to eat. Or a marketing professional may want to know how sighted people's reactions are to an image, such as, does this picture look scary? So what's been done so far in this problem of trying to answer visual questions, we have seen work come out both in terms of human-powered systems that are being used today largely by people who are blind. And there's also been quite a bit of effort in the research community from the machine learning people trying to figure out how to design automated systems. And just to highlight one of the first systems that came out called VizWiz, in this popular system that was used between 2011 and 2015, it was reportedly used by over 100,000, it was reportedly used to ask over 100,000 visual questions, and typically 3 answers per visual question were collected from the crowd. So here I'm showing 10 answers for each visual question that we were collecting from 10 unique crowd workers on Amazon Mechanical Turk. And our work is inspired by 2 key observations about these answers. The first observation is that different people can all arrive at the same answer. So for example, all 10 people agree about the question, is my monitor on, that the answer is yes. In such cases where the crowd agrees, time and money is wasted on trying to collect redundant answers. The second key observation is that a single answer may be insufficient to answer the visual question because the crowd can offer different answers. For example, the question, which side of the room is the toilet on, is ambiguous. Some people say it is on the right, likely because the toilet is positioned in the right side of the image. Others say it is on the left, perhaps because they imagine standing in the room and seeing the toilet on their left side. And yet another perspective is that the toilet is in the middle of the room. For such cases, it's not necessarily clear how in general we should respond to such answer differences. And so the goal of the work that I'm going to discuss today is thinking about how do we efficiently collect all plausible answers. So I'm going to talk about 2 ways that we have considered in my research group. The first is based on the idea of learning to anticipate when a crowd will answer a visual question differently in order to more efficiently capture all plausible answers for a batch of visual questions. And then the second is learning to anticipate why a crowd will answer a visual question differently towards helping users resolve answer differences. So diving into the first one, our first approach again is inspired by the observation that crowd answers can match or differ. And so the premise of this work is that redundancy in some cases is wasteful, and in some cases is valuable. So our analysis that motivated this work is based on looking at 10 answers per visual question for nearly 500,000 visual questions. Included were images from the VisWis dataset, which shows visual questions asked by blind users. So these visual questions often address accessibility issues for daily lives. We also examined a data set that was asked by sighted users about high-quality images collected from the internet. And finally, we also considered images that were asked by sighted users about abstract scenes. So this shows here the agreement trends across the 3 data sets we looked at to motivate the work. In total, we analyzed nearly 5 million crowdsourced answers. And we found that across the 3 data sets, that the crowd agree for about 47%. So the answers are differing about half the time. Okay? So in absolute terms, across all this data, this means that nearly $12,000 and over 4 years of 40-hour work weeks were spent to collect redundant answers on the 50% of the visual questions where one answer was enough. So the idea of the first piece of work is we want to be able to predict if a crowd's answers will disagree, or will match or differ. And so we went ahead and did this idea. The first step, of course, is we collected a bunch of data where we had an image, a question, and a label for each example. Next step, of course, is to separate apart to create training data, which then is fed to the algorithm. We explored 2 different flavors of algorithms. One was a deep learning algorithm. One is the random forest algorithm with handcrafted features. And then see how well it does on novel cases that it was not trained on. So given the black box we trained, apply it to new examples, get out the answer predictions, as well as the algorithm's confidence in those answer predictions. Okay? And so we looked to see how well can this work in practice? Can we figure out whether or not a crowd will agree? And so if we just look at the baseline, the best we can do today, which is given an image and a question, randomly guess, we see that that's kind of the baseline performance across 2 data sets we studied. We look at what happens when we look at an algorithm that predicts an answer, how confident it is as kind of a baseline that maybe could do some good, and we found that it actually can do reasonable. But then we look at the algorithms we trained designed for this task, and we see we get better improvement, better performance, and then better performance from the handcrafted method. Okay? So cool, we have algorithms that work. You might wonder, why are they working? What's so predictive in the nature of the data that allows us to know whether a crowd will agree or offer different answers? And so we just highlighted some examples where there's strong disagreement and strong agreement. And the general conclusion we came to is that the way the question was asked, the language, is currently the most predictive. And there's quite a bit more analysis in the paper talking about this idea. So cool, we have this way to predict if people will agree or offer different answers. So we said, then now let's try to use this to think about how do we more efficiently collect answers from a crowd. So the idea is that when we know that people are going to all give the same answer, we want to collect one example. We want to ask one crowd worker to do the work. When we know that the crowd will offer different answers, we want to ask many people in the crowd to give an answer. So that's the idea, and that's exactly what we did. Again, the algorithms we trained offered not only a prediction of whether there will be agreement or answer differences, but also a confidence score in the belief that there will be agreement or differences. So we were able to just rank all the visual questions in a given batch of images and look at our human budget and say, we will allocate only the extra budget where we collect redundant examples to the cases where we most confidently believe there's going to be answer differences from a crowd. So that was the idea of what we did. So looking at some results, this here shows some plots for one of the data sets we looked at. Results are similar on both of the data sets we tested. It shows what happens when we don't collect any redundant answers. So one example for every single visual question in the data set gets you just above 60% performance in getting the diversity of all plausible answers that are available for all those set of visual questions. 100% is where every single visual question, we collect 5 answers per visual question and look at how many of the unique answers are in the final set. Get above 90%, and in between is where we decide which examples get 1 versus 5. Key take-home point is by using this approach, we were able to accelerate capturing diversity by 23% compared to if you use the baseline VisWiz system that was being used by people to collect 3 answers per visual question in general. That translates to eliminating over 11 40-hour work weeks and saving $1,800 with a very low pay. So we also explored a subsequent piece where we noted that we can get further performance gains if we figure out exactly how many answers we should be collecting. So we explored, should we collect 1, 2, all the way up to 5, showing this with an example where you can see there's 1 example answers, 2 answers, and then more. We would want to collect exactly 1, 2, 4, or 10. So we did do some follow-up work on that, and we found that, yes, we can do better in figuring out how to use a human budget to get all the unique answers. Okay, so the next thing we explored is we said, okay, that's great, but we don't really understand why there's differences. We're getting all the plausible answers, but do we really want to do that? So the next question we explored is the next problem we explored is learning to anticipate why a crowd will answer a visual question differently. And that can be helpful in supporting users to resolve answer differences. Okay, so motivation, again, we have 3 examples here. When does this expire? Does this picture look scary? Which side of the room is the toilet on? What's interesting is the reason that there are differences is different for each example. Okay, so the first one is the answers are all accurate. They're all fine. They're just synonyms. Second one, subjectivity. We heard an earlier talk about this. And then the last one is ambiguity, where all are viable reasons. Okay, we did a literature survey to try to figure out what are people saying are the reasons why crowds differ in providing answers. And we also looked at our data set. And we came up with the following categories of reasons for possible answer difference. So everything from synonymous answers to subjectivity to ambiguity, which we talked about. Spam, of course, is part of why answers differ. Sometimes, if you have a blind person, the evidence is not in the image. You can't find the answer in the image. Sometimes it's just really hard, and you need to find someone who has the domain expertise. Sometimes the quality of the data is so poor that it's difficult to find the information. Sometimes the question is just invalid. It's not a question. And sometimes people offer different levels of granularity and why they're giving an answer. So what book is this? Someone might just say Maxi AIDS. Someone might say Maxi AIDS with some of the subtext underneath it. Okay? So given that, we said here's our taxonomy of reasons. We looked at visual questions from 2 different data sets, one from real people who are blind, one that was curated but is kind of the most popular data set in the machine learning community for visual question answering. And we looked at the examples where the 10 answers do not match, and we collected labels from crowd workers on what were the reasons for the differences in the answers for all the visual questions. And what we found, looking at the 2 data sets as well as looking at them combined, you can see on the x-axis each of the reasons. The y-axis is what percentage of visual questions were classified as having that reason for a disagreement. We found that approximately 20% of the answer differences arise because of the question image pair alone. What that means is that the question image pair could be modified in order to arrive at a single valid answer. The most common reasons for answer differences were ambiguity, synonymous answers, and varying levels of answer granularity. Interestingly, the least common reason is spam, and it was at about 1% for both data sets. Moreover, just to note, the trends were similar both on the data from the real users of a visual question answering system, so from people who are blind, as well as from that fake data set. So that suggests that even these fake toy data sets are valuable to see trends in the real world. We then created a system. System takes in an image and a question, goes through some deep learning mechanisms, and outputs what are going to be the reasons for answers to differ, if any at all. Key idea is we took a system that predicts answers, and the idea was that these systems that are trying to figure out how to give an answer already are learning some idea of when answer differences are going to arise. Built the system, evaluated it, did it overall, as well as for each of the different categories. And what we found is that overall, when we compare our method, the first three are some baselines. Next one is predicting from the image alone, question plus image plus answers that are predicted, and so on. And overall, we see the method does quite better for compared to the baselines. We also found promising results and the ability to detect when a person could either take the image again or ask the question again. So this is something that means that a person who is blind with a phone can snap a picture again, instead of having to wait 17 seconds to learn from a remote person that there was a problem, right? In terms of cases where the algorithm does not do well, it's typically for difficult or subjective visual questions. Not entirely surprising, because these are more abstract concepts. And so thinking about how do we embed common sense into algorithms is an important next step. So just taking a step back, why could this be useful? One, of course, is for some of the categories. You can tell the person asking the visual question how to modify the visual question. You could also decide when to recruit more costly experts. You could also figure out from the many aggregation schemes out there that try to figure out from a collection of responses from a crowd which to deliver. We could figure out which scheme to employ. And also, in the space of designing algorithms, we can rethink how we do evaluation for algorithms. In the case of evaluation, when you're looking at synonyms, every answer should be right. Same with subjective and ambiguous. Every answer should be right. So that wraps up some of the work that my group has been doing. There are a number of people here to acknowledge, as well as funding from NSF for this work. And just to summarize, so we found that a crowd's answers do often differ. In fact, it's about half the time for the data sets we looked at. We talked about some novel problems and algorithms for predicting when, to what extent, and why answers will differ. And also suggested that it's possible to collect the diversity of plausible answers more efficiently. I would like to leave you with the idea that this is just a case study. What we are seeing here is not just true for visual question answering. I believe it's going to be true for many other problems we're exploring as a community. And I hope we all can start to think about these answer differences and automatically providing feedback to people about why they will arise. So thank you.
We have time for a few questions before the break.
Hi, this is really fascinating research. And one question I have, it seems like it's kind of the Q and A, like a lot of discussion about the answer aspect, like predicting when and why the answer would have a divergency. I'm kind of curious if through the research or through the findings so far, whether you have some thought about like future work in terms of helping the people with visual impairment to better construct their questions, or like having the machine in a way to like giving them like initial feedback, like ways for them before, sending out the question?
Great question. So we are actually working on that part of it. I believe, so part of it is just defining the problem, which is what we try to do. Part of it is coming up with automated solutions to help not only identify the problem for us as researchers, but inform users of systems. And then I think a lot of it is also an HCI problem. So, one of the things that you saw is our current algorithms can do a good job, but they're not perfect. So how will users feel if we make them over and over take new images as an example, or keep re-asking the question if we don't have perfect algorithms? What is the level of performance we need from an algorithm to make it useful for an end user? Also, figuring out how to help a user gracefully is important. So, how do you tell someone that the picture is poor quality and help the person figure out how to take a higher quality image? Or teaching someone how to ask questions that aren't ambiguous. I mean, I have that problem in my daily life, right? I ask a question and someone doesn't give the answer I'm thinking of. And so I think there's also just a lot of HCI considerations to take in. And then I think within the theme of what we are seeing today about human-AI collaboration, sometimes we find that the tasks are easy and can actually be done by algorithm. So figuring out how to take those easy examples and send it off to, in theory, cheaper algorithms versus deciding to go to more costly crowd workers versus going to experts. So these kind of hybrid system designs for actually getting the responses.
So I had a question around, I guess you could put this under the banner, like how do we Nazi-proof our like AI collaborative kinds of systems? So you're working in a context where it's like everyone's acting in very good faith, and you're making decisions about how to sort of allocate this labor, and you've got different kinds of tasks. But like imagine a context where you have your algorithms like sending work out to a crowd, and that crowd's been compromised or infiltrated, or you're working in a task where you're making decisions about medical or judicial decisions that like the crowd is making for some reason. When you think about building these kinds of hybrid systems, like how do we sort of harden, or have you thought about how we harden our like AI? Maybe this is a question for Corey too. How do we think about hardening these systems from sorts of malicious actors?
Yes, so that's an interesting question, and it's something I think about because a line of work that goes on in my research group is actually taking images and synthesizing new fake content in images for good purposes, but it could be used for bad purposes. So yes, I think about it. I might, I'm trying to think if I want to punt till we're in the group session versus answer that now, because it's a very good question. Maybe I'll just take a quick kick at it now, and we'll revisit that as a panel. So we know, because we as a community are learning how to develop fake content and corrupted content, we can actually make algorithms that can start to detect that. So that means we need to be aware of the fact that this is a possible situation, and also have algorithms that are notifying us about the quality of our data. So I think it's something extra that is not one of the categories here, but we would hope to see an algorithm that is doing a review of whether or not there's some malicious intent. And we can know from alteration, we can look for trend, there's patterns in corruption. So, thank you for the question.
Can we take one more question and then go to So kind of slightly different than reasons. Are you also looking at actions that would resolve things? So in the case of like the one picture of something that you put up that was in a bag, I wasn't quite certain what it was. And as a human, like if you were showing me video, I would say, can you shift it a bit? Can you show me the back, right? But things that would cause you to change the image. And even if we could get algorithms to generate those kind of things, yes, I'm not certain what this is, but give me a different perspective on it, can be useful guidance for someone that they can respond to. Are you also looking at those kind of like taking action to resolve my uncertainty?
Yes, so we are just starting, so this actually relates to the response I had for an earlier question, and the answer is yes, we are starting to explore that. I think that we are starting to explore it. I hope with us releasing the data set, others will explore it too, because I think this is not a trivial problem. This has human factors involved. takes, it's a collaboration between people who are developing algorithms, people who are developing mobile phone applications, and people who are doing human subject studies. And I think it really takes a large team to explore it. So we are doing that. We actually have collaboration with Microsoft that's starting to think about some of this work. And all the data will be provided freely so that others can also take this up and do more work. So I don't, does that answer your question? Or?
Goes through it, yeah.
Okay. Great. Thank you.
Can I just add a squeeze in a question? Sure. Question. So it's so exciting. So it seems like such a fertile space for exploring all different ways of kind of configuring humans and machines. And I think that's what's so fun in general, about this kind of work that many of us are doing. And so, so the idea that came to mind, I wanted to ask you, have you looked at computer-mediated collaboration as a way to resolve some of these differences? So I don't know if you know the ESP game. Yeah, so some version of that allows people to kind of asymptote toward a common view, have a real time, which also incentivizes the participation because it's kind of a game. It's fun to do something like that. Yeah.
Yes, so I agree that that's a really exciting fertile space. Actually, I think that AJ's work earlier, where she talked about revolt, is a starting step in that direction, if that's the right paper I'm thinking of. So there are just little seeds of this kind of work emerging. Yes, I have thought about it. Yes, I would love to do it. The work has not been done, so.
Right, so there are 100 ways to slice and dice it, and then picking which one to pursue, and also having the tools that make it easy, both to sort of aggregate these methods, enact them within a system, make them reusable, and then, each of us can sort of, we develop a taxonomy of these things. And then it's not like we're brainstorming de novo every time we have a new system. Well, how should we combine the machines and the humans? We start to develop a sense of, this is the, these are the classes of ways we can combine these things and kind of come together as a community to sort of formalize that stuff and make it easier to move forward.
Yeah, and I think a lot of that is going to be a lot of benchmarking and brute force work to understand where do algorithms do well, where do humans do well. This was the last talk, the point of really understanding the strengths and the weaknesses of the characters. Definitely.
But I think it's also very context dependent. So, where the humans are strong and the machines are strong in one context could be upside down in a different context, depending, right? So, I mean, it's such a complicated space. Good luck to all of us.
I'll close it with that. So we'll meet again at 10:30, okay?